Hello, my name is Liam and I'm a 2023 Pawsey intern with a background in mathematics and machine learning. My project aims to enhance the stability of diffusion neural network potentials in low data settings. Conducting molecular dynamics requires a function that calculates forces on atoms from their coordinates to find their new coordinates over time. Classical MD is very fast but relies on fine-tuned parameters and hence is harder to generalize to simulate new systems. Ab initio MD works by calculating forces by solving Schrödinger's equation. This method is easy to generalize but can be slow for big systems. Training neural network potentials on a dataset of coordinates and pre-calculated force data provides a promising avenue for fast and accurate MD. New diffusion-based neural network potentials can train without force data, however they tend to need more coordinate data for stable MD. My goal is to boost the stability of these diffusion neural network potentials in low data settings by expanding the dataset using a simple duplication trick. We test the models on simulating coarse-grained lithium chloride in water at 300 Kelvin. The way these diffusion models work is by adding noise to the coordinate data and training a neural network to learn to go from the noisy coordinates to the negative of the noise that was added. The duplication trick that we're doing is taking the coordinate data and adding two different sets of noise to it to create twice as much noisy coordinate data. We then stack this data and train the diffusion model on this larger dataset. Now, how is this giving us forces? The intuition is that adding noise is making the system more disordered, and learning the negative of the noise is learning how to go back to the slightly less disordered or more stable state, and this is exactly what forces do. We then train two diffusion network potentials on the same set of coordinate data, one with and one without the data duplication. We also train a traditional neural network potential on actual coordinate force data and use that as a benchmark. To test the stability of these models, we run molecular dynamics using them and compare the radial density functions, which are kind of like histograms that plot the frequency of distances between specified atom types. We chose to work with 500 frames of coordinate data for the diffusion models and 3000 coordinate force data for the benchmark neural network potential. The plot here shows the regular diffusion model's RDFs compared to the benchmark in the top row and the augmented ones in the bottom. The regular diffusion model produces huge spikes in the 0 to 2 angstrom range, implying high instability. However, the augmented diffusion model has completely eliminated these large spikes and is conducting much cleaner and more stable MD. It's very exciting that from the same coordinate dataset, a simple duplication technique completely removes this unstable behavior. The main impact of this project is highlighting the potential for running neural network potential-based MD with considerably less data. An interesting avenue of research is to optimize this data duplication. The duplication process is more delicate than it seems. With smaller variance in the noise added to the coordinates, the duplicated data is too similar and causes overfitting issues. However, higher variances lead to inaccuracy in the diffusion model. Trying to balance the duplication and the variance could lead to a greater reduction in the data required for a diffusion model.